Hello everyone, welcome to my YouTube channel. If you're watching this, chances are you're feeling some serious pressure right now because of AI. AI is everywhere. Your company is talking about it. Your industry as we speak is being disrupted by it. Your friends and colleagues seem to be moving very fast with it. And somewhere in the middle of all of this noise, you're still trying to figure out, what does this actually mean for me? Where do I even start? On top of all of this, the terminology alone can sometimes feel like a wall. Data science, machine learning, deep learning, LLMs, language models, large language models, agents, agentic AI, so many buzzwords. You might be wondering, are they all referring to the same thing? If not, are these all even related? And if so, how? What is the connection between all this? If any of that sounds familiar, well, this series or this playlist is for you. Through this AI careers playlist, I want to guide you. Most importantly, I want to walk with you step by step through everything you need to know. You need to understand and learn so that you can navigate this rapidly evolving AI landscape with confidence. Whether you're transitioning into AI, upskilling in your current role, or just trying to make sense of what's happening around you, this series hopefully will give you the clarity and the direction you need. But see, before we can decide on what to learn or which career path to choose, before any of that makes sense, we first need to understand how all of this actually fits together. So in this video, I'm going to take you through this complete AI story, where it all began, how each piece evolved, and how data science, machine learning, deep learning, language models, large language models, and agents are all connected. Not as separate, disconnected buzzwords, but as one continuous journey that brought us to where we are today. By the end of this video, I promise you, the fog will lift. Maybe at least a little. You will see the full picture clearly, and from that clarity, everything else we cover in this series will make complete sense. Let's get into it. Okay, let's first talk about data science. In a way, it all started with Harvard Business Review calling data scientists the sexiest job of 21st century. This was in 2012. So you may ask, why? What is so special about data science? Well, data science is special because it focuses on the science, or rather the art, of extracting insights or intelligence from data. Just like mining gold or oil, but now intelligence from data, and who doesn't want intelligence, right? So think of data science on a high level. The main focus is building or training these models. These models that feed on lots of data. When I say lot of data, think of volumes of data and also varieties of data. Okay, so all of this data is fed into the model, and we train the model. And once the model gets trained or becomes smart, right, then we leverage these trained models to make intelligent decisions. What kind of intelligent decisions? Well, we could use these trained models to make, predictions, pattern recognitions, and many different kinds of intelligent decisions. So this is your data science on a very high level. Okay. In practice, of course, data science, it's a combination of subdisciplines like statistics, math, programming, AI. Okay. But for now, let's keep things on a very high level. Okay. So in a nutshell, data science is all about building these models that can feed on different types of data, become smart, and then make intelligent decisions. Simple enough. Okay. Next, we're going to take a closer look at these models. How do these models actually look in practice? Okay. All right. Let me first take a simple example of house price prediction. Let's say we want to build a model that can predict house prices. Okay. So we want a model. How do you build this model? As I just explained, right? We want to feed a lot of data into this model to make it smarter, to train this model on the data, right? You may ask, what kind of data? Well, think about the house price. If you want to build a model that can predict house prices, what kind of data set we may need? Maybe something like this. Maybe we want to use, the square foot of a home, the number of bedrooms maybe, the lot size maybe, right? So this features, right, this square foot, bedroom, lot size, we call these inputs. Okay, so whenever we're training the model, we give the model these inputs. Also, we give the outputs. Meaning for this home, this first home with 5,000 square foot, 5 bedrooms, 1.2 lot size, the home price is 350K. It's a known value. Okay. Now in reality, if you're building a house price prediction model, let's say Zestimate in Zillow, you're going to use a lot more features, right? Not 3. So you're going to use like hundreds and hundreds of features. So not just 3. But for our example purpose, let's keep it simple. Okay. All right. And also if you see, I have chosen like how many 6 samples. Okay. In reality, if you want to train a model that can predict house price, you want to give the model as many samples as possible. Think million house samples. Okay. Okay. Hopefully you got the idea, right? So the main thing is we give to the model this inputs, which I'm calling X. Okay. And the outputs, which we are trying to predict, I'm going to call it Y. Okay. So the model feeds on all of this data. Again, say million house samples, right? And it gets trained and becomes smarter. So once the model looks at all this data, it became smarter, right? Now we're ready to make some predictions. But let me explain. This process of feeding all of this data into the model and making it smarter is called training the model. This process is called training. Okay. All right. So once the model is trained, then we can feed a new unseen sample. In this case, I'm giving 2 house samples, which the model has never seen. Okay. Again, I'm just giving the inputs X. And when we give this inputs, because the model is already been trained on this, humongous volume of housing data with inputs and outputs, now it can make prediction, and it makes hopefully the right predictions. The house prices for these 2 unseen samples. Okay. So this process on the right, we call it like all of this thing where we're making predictions is called inference. Okay. This is important, the training and inference. Because nowadays, many of us are using ChatGPT and all kinds of AI models, right? Remember, anytime you're using an AI model, what you're doing is you're doing inference. Anytime we're building the model, we're doing training. So whenever you use an AI model, right, you're not training anything. You're just simply using it. And that's called inference. Just wanted to explain that. Okay. All right. So on a high level, hopefully you can see, right, how a model is actually trained. You give inputs and outputs. You use that, again, a lot of that to train the model. Once the model is trained, then you feed it unseen data, right? And then you make predictions. Okay. So this was a simple house price prediction example. Let's look at a few other examples. Let's say image classification. So how would the data for an image classification look like? Again, let's say we want to build a model that can classify different images into cats and dogs. Okay. So we want to build a model. So the data, again, will look something like this, right? So we give inputs. Okay. So we give inputs and we give outputs. Okay. Now, what are the inputs? The actual images of cats and dogs. And for each image, we have a corresponding label, cat, dog. Okay. So this is our data set, the input. Or again, what we give to the model, the inputs and outputs. Okay. Now, if you want to build an image classification model, again, just like for the housing example, you want to feed the model as many samples as possible. Say 1 million images and the corresponding labels. You train the model becomes smart, right? And once the model is trained, then you give it an unseen image, like let's say this image of a dog, and the model correctly predicts it's a dog. Okay, hopefully a little bit more clear. Just one more example here. Now let's say we want to build a model that can do sentiment analysis, like sentiment classification on some kind of reviews. It could be patient reviews, customer reviews, product reviews. So again, we want to build a model. We need to feed it a lot of data. Again, if we are saying, like, let's say it's a product review, so we give inputs. Our inputs are nothing but the reviews, the product reviews, amazing service, very satisfied, worst product, and so on. And then we give the corresponding labels or outputs. In this case, the sentiments, positive, negative, neutral. Again, imagine we give 1 million of these product reviews to the model. The model gets trained, it becomes smarter. And then you give it a previously unseen review arrived late and in bad condition, and the model correctly predicts that sentiment as negative. Hopefully, these examples make it clear. I'm using different examples here, right? Housing price prediction. That's I'm going to go little deeper into the actual algorithms little later. But for now, on a very high level, we saw 3 different examples: house price prediction, image classification, sentiment classification. What is the common theme here? We train a model by feeding it a lot of inputs and outputs. Model becomes smart. Now the question is, how exactly it's becoming smart? What exactly these models are doing? Those models are actually forming a mathematical relationship between X and Y. So between X and Y, we are kind of forming a mathematical relationship. How does this mathematical relationships actually look like? Well, that's where AI come into the picture. We use AI to build this relationship and to train the model. So I'm going to explain that a little bit in more detail than later slides. Okay, let's take a look. Okay, so again, we build or train these models using AI algorithms. So when I say AI, of course, it's artificial intelligence. So how big is this artificial intelligence? And how is this connected to machine learning, deep learning? Well, I'm going to explain. So this field of artificial intelligence, it's not new, right? Research in AI has been going on since 50 years. In the early years, when we said AI, we meant symbolic AI. This was the dominant paradigm until 1980s. So what is a symbolic AI? Well, in symbolic AI, we humans handcrafted rules and logic to teach machines as to how they should perform. And as you can imagine, if we are defining these rules as to how the machines should act, very soon it became clear that this approach will not work to reach human level intelligence. That's when machine learning, which is again a subfield of AI, became the face of AI, again since around 2012. Okay, now what exactly is machine learning? For now, as I said, it's a subfield of AI. I'm going to explain machine learning in more detail in the later slides. But for now, think of machine learning as this field which has all these algorithms, or many of the algorithms, to build the models. So all these algorithms which form the mathematical relationship between inputs and outputs, think of those algorithms are present inside machine learning. There are many different algorithms in machine learning which we can use to build these models. I'm going to explain that a little bit in more detail in the later slides. Okay, so that is machine learning, a subfield of AI used to build these models. Then what is deep learning? Well, deep learning is also part of AI, subfield of machine learning. Okay, now deep learning is nothing but comprised of neural network algorithms or neural network models. But see, this neural network models became so popular for certain types of data, like unstructured data, images, language, that deep learning itself, grew big and became the face of AI. In a way, deep learning made ML the face of AI. Okay. Again, I'm going to explain what deep learning is in more detail later. But for now, just for context, think of deep learning. Anytime, again, we're using any AI model, whether it's ChatGPT, Claude, Gemini, agents, whatever the buzzwords you're hearing right now with respect to AI, the foundation, all these models at the end of the day, the core technology, they're built using deep learning. So it's that important. I just want you to appreciate that. Okay. All right. So we have seen what AI is on a very broad level, how machine learning became the face of AI since 2012. And now deep learning made ML the face of AI. But at the end of the day, when we say AI, it's deep learning. It's all neural network models where we are going right now. ML is still useful. I'm going to explain that. Okay. All right. Now that we understand this, let's take a closer look at machine learning. Okay, let's now understand machine learning with this house price prediction example we have already seen. So what was the intuition here? Right? The main goal was to build or train these models that can feed on a lot of data. In this case, a lot of housing data become trained, become smart, and then we can make predictions on this using this trained or smart model. Okay. Now the main question is, how do we train these models? Okay. Now, when it comes to AI, not just machine learning, right? Any AI model, any time we're talking about building a model or training a model, all we're doing is trying to form or predict optimal mathematical relationship between our inputs X and outputs Y. That's all we are doing on a very high level. That's what is happening. These models are trying to come up with a mathematical relationship. So whenever we say how do we train these models, we're talking about building this relationship or trying to find this formula. Okay, something like this on a very simplistic level. So y pred, again y that we are predicting, is equal to a function. F is just a function, any kind of function of X. So this applies to any AI model, whether it's machine learning, whether it's deep learning. The only difference is in how complex this relationship is going to be. Okay, so let's say now if we want to use machine learning to find this relationship, how would that formula look like? Now for this particular example, house price prediction example, we can use an algorithm called linear regression. Now in machine learning, there are many different algorithms we can use, right? But for this particular problem, let's say we use a linear regression algorithm to find this mathematical relationship. And if we do that, the equation may look something like this. Y pred equal to W1 X1 plus W2 X2 plus W3 X3 plus and so on. Again, we're using 3 features here: square foot, bedroom, lot size. As I said, you could use hundreds of features, right? And if you use those features, again, it will continue this equation. Now, I wanted to keep things simple on a high level, but I have to deal with some math here because I want to explain some important concepts, okay? Especially a concept related to weights or parameters. Why? See, some of you or many of you might have been hearing about all these AI models being billion parameters, trillion parameters, weights. Well, what are those weights? Well, those weights are these. So let me explain this concept a little bit more so that it clicks. So this relationship you're seeing, right? Y pred equal to W1 X1 plus W2 X2. This is a simple linear relationship. At the end of the day, all we're trying to do is we're predicting this Y using X. Now the key thing here is these weights, W1, W2, W3. Okay. All right. So what this formula is telling us is, as we choose the X, right, the square foot, bedroom, lot size, for a given X, what is Y? That is determined by these coefficients W1, W2, W3. And the algorithm, in this case, as I said, we use linear regression. Linear regression is the algorithm, which gives you this formula. So this algorithm, as we train this model on this vast amount of data, it automatically looks at all these examples, say million samples. It looks at all of this. And then it determines these optimal weights that will give us a perfect or a very good formula. Once we get this formula, then you give it some new unseen input X, it's going to predict your home price correctly. So hopefully the intuition is a little bit clear. Okay? Please don't worry about the math, right? If any of the math is rusty, but focus on the high level concept here. What is high level concept? AI model means finding mathematical relationship between inputs X, outputs Y, period. Whether you're using house price prediction, image classification, sentiment, language, whatever. That's what on a high level is happening. If you say AI. Now within AI, right? If you use machine learning, a relationship between inputs and outputs, for example, in this house price example, could look something like what we are seeing here. And the key thing is these weights. Any relationship, there are weights involved, there are parameters involved. What are these weights? What are these parameters that are giving us this great relationship? So that's the key intuition here. Hopefully it makes sense. All right. So now the next question is, when do we use these machine learning algorithms? Well, anytime features are readily available. What do I mean by that? For example, in this case, with the house price prediction data set, as I said, we could have 100 features, right? Let's say data scientist was building this model. Out of the 100 features, like square foot, bedroom, lot size, crime rate, pollution, school districts, whatnot. Out of all this, he may say these 3 are important or these 10 are important. So we humans, or a data scientist or a practitioner, is giving this data set to the model, right? He's giving this data set to the model, but inside that he's saying, okay, these 3 features or 10 features are important, use them. Okay, so that's what features are readily available means. This is also called feature engineering. So whenever Using our human intuition, if we want to build a model, we have a data set, but inside the data set, out of all these features, we can tell which features are going to help the model, right? We are doing feature engineering. And if you think there is a problem or use case, we can do that. We use machine learning. Machine learning will be very faster, very accurate. And also we use machine learning, especially if you have structured data. As you can see here, right? This is a table, flat file. Anytime you have structured data, think machine learning. Also, it's ideal for smaller data sets. Machine learning is also very, very fast. I know nowadays we're all fascinated with LLMs, agents and all that, but trust me, there are many use cases, many problems where machine learning still works great, very faster, and the return of investment, or the ROE, the effort you put in, is going to be much greater with machine learning, the classic machine learning. Okay. One more thing though, ML algorithms are shallow. So what do I mean by that? Well, by shallow, I mean when we're building this relationship, as you can see here, right? We are directly using the X as is, right? Whatever the X, we select the features, we do the feature engineering, but this X1, X2, X3, we give this to the model and we're saying, okay, build a relationship. We go from X inputs directly to outputs Y. That's a little bit of shallow. In contrast to the deep in deep learning, which I'm going to explain later, and then this concept of shallow and deep becomes more clear. Okay, all right. Next, so this was just one example, right? House price prediction. This is in particular related to something called regression. Regression is anytime your target variable, like this output which you are predicting, is continuous, right? 350k, 285, anytime it's like use regression algorithms. Or anytime your target variable, this output, is discrete, meaning pass or fail, win or lose, disease or no disease, right? Then you use something called classification. But in this video, my goal is not to go deep into all of that. I just want to give you the intuition on a very high level. Okay, what exactly we mean by machine learning? It's building a mathematical relationship between inputs and outputs. With machine learning, you have a library of algorithms you can use, and anytime you want to form this relationship directly between X and Y in a shallow manner, use machine learning. Also, whenever the features are readily available and when you have structured data. Okay, hopefully that is clear. Next, as I said, this was for house price prediction example, but there are many other use cases you can use machine learning and it will work great, like predicting sales, forecasting, disease detection, fraud detection, spam classification. Okay, hopefully now you have a good feel as to what machine learning is. Okay, next, what we're going to do is we're going to look at deep learning. Particularly, we'll understand deep learning initially with image data. Later, we will also look at deep learning with language data. That will slowly start, progressing. You can see the progression towards LLMs and agents later. Okay, but for now, let me explain in a step-by-step fashion. So we're going to learn deep learning, okay, with respect to image data. Again, the image classification problem. We saw this, right, in the earlier slides. So again, let's say we want to build a simple deep learning model from scratch that can classify cats and dogs. Again, as I said, we feed a lot of these examples, right? Raw images, so of cats and dogs to this model. We train it, it becomes smart and it can make predictions. Say again, you give it 1 million images. Okay, all right. So now the question is, how do we train deep learning models? So can you guess, how do you think? Again, the goal is to build this model, right? By feeding this data. How do we train this model? Well, mathematical relationship, right? These models are building a mathematical relationship between X and Y. Okay, something like this. Okay, we just said that this is what we do with machine learning, right? How is deep learning different than machine learning? In machine learning, we used a formula, a linear relationship directly between X and Y, right? Something like this. But see, as I already striked it out, for deep learning, it's a relationship between Y and X, but it won't be that simple like this linear relationship. So, 1 second. So cross this. So it won't be this simple. Okay. So if it is not that simple, how do we form this relationship between inputs and outputs, X and Y? What kind of shape does it take? Well, what happens is with deep learning, again, with machine learning, I said those algorithms are shallow, meaning directly we find a relationship between input X and Y. But with deep learning, we don't do that. What we do is we take these inputs X, we transform it. We transform it into more meaningful representation. We let the algorithm, deep learning algorithm, automatically extract important features. through these transformations and then predict why. Lot of words. Hopefully the visual might help. Okay, so this visual is from Francois Collet, the author of Keras. So in this one, again, he has this visual. I love this visual. So hopefully this will make it more clear for you. So what we do in deep learning is, let's say, again, we start with our inputs, X, let's say cat image. I'm just going to explain with a simple one single image. Okay, we do this again for all the million images simultaneously in deep learning, but just for one image. So instead of directly using this cat image, again, when I say cat image, what is this? What does a cat image has? Pixels. These are the raw pixels. Okay, so you can take these raw pixels, right, and that's your X, and you can predict this using the raw pixels as this is a dog or cat. You can do that too. If you do that, then you're doing machine learning. But with deep learning, we don't do that. What we do is we take these raw pixels of this cat, we transform this input data into more meaningful representations through these intermediate layers called hidden layers. I'm showing you two layers here, L1 and L2. And then we predict why. Okay, what are we doing here? What we're doing here is, in deep learning, we transform this input data, input image of cat, into more meaningful representations. For example, this L1, what this layer is doing is it's capturing more finer features like the curves, the whiskers, the edges. That's what this L1 is doing. Now L2 is capturing more aggregated features like maybe the eyes, maybe the nose, maybe the ears. You see, hopefully you get the idea. So again, in the housing examples, right, with the housing data, we are telling the model that in this entire housing data, maybe there are thousands of features, but square foot is important, bedroom is important, lot size is important. But with deep learning, we don't say anything. We just say, here are the raw pixels. Take this image. Now what the deep learning, which is a neural network model, what it will do is, it will first transform this input data X into other representations through this intermediate layers. So this L1 is capturing finer features, L2 is capturing more aggregated features. Then we make the prediction that it's cat. So all these transformations, as you can see, it's helping the model to predict that this image actually belongs to a cat. So what about the relationship then? Well, we still have a relationship. So you still have y pred equal to, it's still a function. It's still a function of x, but it's first function of L2, right? This y is function of L2. My bad, let me do it here. So you're still doing y pred equal to function of L2, this layer L2, which is a function of L1, which is a function of x. I know this is some kind of might look some intimidating math equation, but what I'm saying is this y is dependent on L2, L2 is dependent on L1, L1 is dependent on x. If it was just machine learning, directly y is dependent on x. You find a formula like that. You're still finding a formula between y and x, but using these intermediate transformations with L1 and L2. Okay, so on a very high level, that's what deep learning is doing. Transforming the input data into more meaningful representations. And in the process, it's automatically extracting some important features. We are not giving those features by handcrafting them. The deep learning algorithm, the neural network algorithm is figuring it out. And because of that, it is able to do a much better job than a classic shallow machine learning. And hence the deep in deep learning. And what I'm showing here is just two layers. Again, when you say deep, with the deep neural network, you would have many layers. Okay, hopefully the intuition with respect to deep learning algorithm is more clear. But just to cement it, in machine learning, we figure out what matters in data and we tell the model, right? We do feature engineering. In deep learning, the model figures these features itself through these intermediate layers, layer by layer. Okay, hopefully now you have a very good understanding of what deep learning is and how it is different than a classic shallow machine learning. Okay, next, I'm going to talk a little bit more about deep learning again with image data, just to make these intermediate layers concept more clear, because visualizations can help. So here I'm showing you a simple example. Previously, we were building a model that can classify cats and dogs. Now, say we are building a model that can classify digits, images of digits. So here you have a raw image of 4, right? So we are classifying, say, this raw image of 4 as with the actual label 4. So there are 10 classes, digit classes 0 to 9, right? Again, the goal here is I want to show you how the image transformations actually look like through these intermediate representations. Again, layer 1 may be capturing some finer features. Layer 2, some again finer, some aggregated. Layer 3, more aggregated features. And combined, the raw image and all these intermediate representations, right? They're extracting different features from the raw image. We are predicting that this image actually belongs to label 4. Okay, just one more example. Hopefully this makes this intermediate layer representations even more clear. So let's say again we're building a face detection model. So I haven't shown here, but let's say what will be the X? X would be your human images, right? Let's say all kinds of faces, many million faces, and the corresponding labels. And the labels, let's say they go here, Y. Okay. So now I just want to show you how the intermediate layers actually look like. See some of the earlier layers, right? You transform these face images, right? Out of all of this, these early layers are capturing some edges. And these middle layers, you see, slowly it's capturing some eyes, some ears, some noses. And finally, these final layers are slowly forming the entire face image. And then we make a prediction that this face belongs to John, this face belongs to Amy, this face belongs to Srikanth. Hopefully, this, what exactly is happening in these intermediate layers becomes clear with these visuals. All right. So let's continue a little bit more talking about deep learning with respect to image data. Well, the reason is I want to talk about one of the biggest breakthroughs that happened in deep learning, where actually deep learning proved itself. So what was that? Well, that moment was ALEXNET 2012. This was in 2012. Well, ALEXNET entered a competition called ImageNet Challenge. What is this ImageNet Challenge? Well, this ImageNet challenge, it had 14 million images. And the challenge was taking a subset of the images, like 1.2 million images, and classify them into 1,000 different categories. Whichever model performed best, it won the competition. And before ALEXNET came in 2012, the state of the art, one of the best models in this challenge, were using classic shallow machine learning based approaches. Now, with ALEXNET, things changed. So what ALEXNET did is it used deep learning instead of machine learning. And it used 8 total layers. In the examples earlier in the previous slides, I was showing you 2 or 3 slides, right? Now, this it's in practice, this has happened. This was the biggest breakthrough. ALEXNET used total 8 deep neural network layers. Okay. And with that, it completely destroyed the competition by giving an error rate. The performance of the model, the error was only 15.3% compared to 26% of the next best competitor. That was almost only 50% reduction, 40 to 50%. And that was dramatic at that time. And at that time, many people were not taking neural networks or deep learning that seriously before this moment. But when ALEXNET showed what is possible with deep learning over machine learning algorithms for image classifications, everybody started noticing. So this was, in a way, one of the biggest earlier breakthroughs in deep learning. There are a few other more I'm going to talk about in later slide, but this is one of the very, very key moment, the ALEXNET. Okay, all right. My bad. Okay. Now, then once ALEXNET showed what is possible with deep learning, many researchers started building on it by adding more layers. One of them was VGG16. Again, this visual, I just want to show you how these layers look like. Again, please don't get intimidated. See where we are right now with respect to ML, deep learning, AI. Many of these algorithms, right, even with machine learning, what I showed you, the mathematical expressions, we don't build it. There are readily available algorithms which we just simply use it. Okay. Even deep learning. So don't get intimidated with all the architecture. Just appreciate the intuition. And the visuals I'm providing is to just help you. So VGG16 model, as the name implies, it uses 16 layers. Okay, it was an improvement on ALEXNET. And see here, the error rate now got even cut into half, 7.3%. So people started experimenting with deep learning more and more since then. Okay. Now, one more thing is what enabled this performance, right? Again, deep learning, but within deep learning, what is it? Well, a new type of, I mean, they're not new actually, this convolutional neural network. So CNNs or convolutional neural networks, they have been there before too. But with this moment, right, when ALEXNET used them, it showed that these architectures are extremely powerful, very fast, and can scale very easily because you can train on many millions of images again using this architecture. So CNNs are one of the earlier powerful neural network architecture mainly that worked for images. Now again, this could be a technical jargon which you might be thinking, oh, you promised to keep this video on a high level, making it easy to understand. I agree, I understand, but see, there are some of this neural network architecture which we as students of AI really need to know, and CNN is one of those. CNNs is what, like, in a way made image classification very popular. Okay, so this is one of the state-of-the-art architecture at that time, so I just wanted you to remember that. Okay, actually they're still being used. I mean, CNNs are still widely used, but convolutional neural networks are what made deep learning initially famous with images. Okay, also the availability of large labeled datasets, right? Here ALEXNET was able to train on this 1.2 million images, and most importantly, what I'm hinting at is the availability of GPUs. See, before there, CNNs were there before, but why the convolutional neural networks didn't become famous before 2012? Because the computing capacity was not there too. So right then, NVIDIA with its GPUs showed what is possible. Again, if any of you is not aware, right, NVIDIA, I mean, I'm assuming many of you might be, NVIDIA is the leader which is enabling the AI revolution today with all the compute through GPUs. Okay. And also there are few additional neural network techniques that went into ALEXNET and VGC16 which enabled this performance, but I don't want to go through all of that at this point, like activation functions and all of that. I don't want to confuse. I want to keep things simple because see, so far the intuition, right, very clear. Machine learning is shallow. We directly go from input X to Y when we can do feature engineering, when we can tell the model which features are important. But we can use deep learning where through this neural network model, through these intermediate layers, deep learning transforms this input data automatically, gets the finer features, aggregated features, right? That's what we talked earlier. And here I'm showing how that idea was further extended to get some big breakthroughs in deep learning through ALEXNET VGC16. Okay, all right. So by 2015, deep learning models were beating humans at recognizing images. Think about that. And modern deep learning models, see, so far this ALEXNET has the 8 layers, VGC16 16 layers. Modern deep learning models can have thousands of layers. Okay, all right. So now the question is, when do we use deep learning? By now already you might be having some idea, right? So we mainly use deep learning for unstructured data like image data, language data, large data sets, right? Whether it's machine learning or deep learning, they need a lot of data, even more for deep learning. Okay, and most importantly, complex relationships between inputs X and outputs Y. The relationship between like images and labels, right? Language, this is all complex relationship. So while classic ML can work, in terms of performance, deep learning is much more going to be superior for unstructured data where you need complex relationship between inputs and outputs. Okay. Another thing is a very important concept of transfer learning. So what is transfer learning? Well, transfer learning is like, let's say this ALEXNET, right? VGC16. Now, of course, ALEXNET was built for ImageNet. It wanted to beat the competition there. But once this ALEXNET model was published, right, VGC16 is published. So let's say we have to build our own deep learning model from scratch, let's say, to classify something else. Like, we want to build some face recognition model or some other image classification model. We have two options. We can start from scratch, right? We have to collect that labeled data set, whatever we are trying to do. Maybe we are trying to classify different humans in our community, the faces, right? So you collect all these images, you label them. That could be a humongous task, right? You start from scratch. You could do that, and you can build a deep learning model with this 8 layers, 16 layers, or whatever. Or you could take these pre-trained models that have already been built, like ALEXNET or VGG16, Now you may ask, wait a minute, ALEXNet and VG16, they might have been trained on a different data set, like, in this case, this ImageNet, right, where you have 1.2 million images. How is that going to be applicable for our own image classification task? Well, that's the beauty of transfer learning. So this deep learning, right, let's say VG16, it has 16 layers. So you can take this model as is, treat it as a base model, and then you fine tune it on our own image classification dataset, which could now actually be very small. We don't need too many samples of images and the corresponding labels, because these pre-trained models, they have captured, because it's been trained on 1.2 million images for 1,000 categories, especially the finer layers in the deep learning, right? They might have captured all the the curves, the edges, certain aggregated features, different visual features have already been captured or embedded in this pre-trained model, this VGG16 or ALEXNet. You can simply use them as base model and fine tune on our own image classification model, which dramatically reduces the training time. So this is transfer learning. Hopefully, you understood what transfer learning is. This is important because we're going to use this. I'm going to explain how useful this is later for when you go to the language modeling. Okay. All right. So this was deep learning with images. Now it's time to talk about how we build deep learning model for language data. Okay. All right. So let's say we want to build a sentiment analysis model. This will be language classification, right? We're going to build a sentiment analysis model, say for product reviews. Okay, so I'm going to show you with a single example as to how a deep learning model could be built around this one. Okay, so let's take one review. I'm gonna keep it simple. Worst product I have ever bought. So this is our input, right? Again, when it comes to images, each image was a sample. Now with language, in case we're trying to build a sentiment model in product reviews, each review is our sample. Okay, and I'm going to call it X. One more thing, in the previous examples when we dealt with images and all the earlier slides, I showed you the progression from left to right. X was on your left side, Y was on your right side. But for language, typically this is how it's shown many architectures, so I'm going to follow that practice. So we're going to go from bottom to top. Okay, so this is our review, and the goal is to predict that this review is negative, okay, as it is obvious. Now the question is, how do we build a deep learning model? See, we could actually build a machine learning model also here. There are certain things we do, I don't want to go into detail, but the concept is we directly build a relationship between X and Y. Okay, now whether it's machine learning or deep learning, these tokens, these words you're saying, worst product I've ever bought, machine learning or deep learning doesn't understand words, it understands only numerics. So before we build machine learning or deep learning, we convert this word into some kind of a numerical representation. Now, going deeper into that is beyond the scope of this video, but I have a deep learning playlist where I explained all of this in more detail. Okay, I'm going to link that in the description. But for now, just focus on the high level intuition. So we could build machine learning. What would that mean? That means we directly go and form a mathematical relationship between X and Y. Okay, but since we're doing deep learning, we're not going to do that. What we're going to do, as you might have guessed, we will have some intermediate layers where we're going to transform this input data into more meaningful representations, and we'll extract certain features. Okay, what do you mean? Let me show you that intermediate layers are basically deep neural network, something like this. Now, all these circles, all these nodes, I mean, if you see this and it intimidates you, what we're going to do is, in this video, right, I'm just going to abstract it away. Okay, this you will understand. We have 3 layers, just like before with images, right? But now for language, so I have L1, L2, and L3. See, 3 layers. So what each layer is doing is, this layer 1 is capturing the grammar out of this sentence. Layer 2, grammar or word pattern, or layer 2 is capturing phrases like worst product ever bought. And then by the time you go to L3, it's getting the full context and meaning. So this is what deep learning is doing. We're giving it a raw sentence, and from that sentence, it's capturing more features that can help this model tell that this review sentiment is negative. Okay, again, intuition wise, hopefully this is clear. So we transform the input data into more meaningful representations, right? And we capture different features like grammar, phrases, full context. Now, what kind of meaningful representations, how we are going to actually represent each of these words into numeric format. Again, as I said, all of that we're going to talk in a later video. Okay. Now, this kind of architecture that I'm showing you here in the screen, right? This is something called, initially the architecture that worked for text data or language data was called RNN. RNN means recurrent neural networks. Okay. But the problem with RNNs was, see, this RNN architecture, it reads this sentence from left to right. So we go like this: worst product I have ever brought. So it reads this sentence sequentially, one word at a time. This architecture, RNN, recurrent neural networks, it worked fine for short sequences. But for very long sequences, RNNs, what happened was, as you kept going, worst product, this is a short sentence, but imagine a big sentence as you kept going, right? Because each of this word is dependent on the previous word, right? So there is some kind of a context, it's some kind of a memory between words. So as you go deep into the sentence, the RNN architecture forgot some of the earlier words. So for long sequences, the RNN was having some issues. Then came another architecture, LSTM, long short-term memory. So again, without going too deep into these architectures, what LSTM did was, okay, what is the main problem of RNN? As it went too deep, it was forgetting some of the earlier words. So maybe I will fix it. So that's what the LSTM architecture does. It fixes some of the memory issues which RNN was having. And LSTM worked great for little bit longer sequences. But even longer sequences, right? To scale this architecture, even LSTM also fell short. Okay. And then something great happened, which I'm going to explain later. Okay. But for now, these were some of the earlier architectures that worked great. But again, please don't get me wrong. LSTM architectures work even fine, extremely well on language and also on something called time series. Okay, so there are many applications where LSTM architectures work well, especially if you want a fast model. Okay, but through this visual here, what I want to show you is just give you this intuition as to how the deep learning, the same concept, right? We transform the input data into more meaningful representation. In the process, we extract additional features automatically. Human doesn't give it. And then we make a prediction on this one, right? So that's the intuition I wanted to provide. And RNN and LSTM neural network architectures were the state of the art around 2017, before 2017, okay? Also, before 2017, another important thing was researchers or practitioners were building separate deep learning models from scratch for each NLP task. What do I mean? For example, NLP is natural language processing, right? NLP means NLP, natural language processing. So sentiment analysis is one NLP task. So researchers or practitioners were building a deep learning model from scratch using these architectures for sentiment analysis. So if you want to say build a model that can answer questions, right? QA, you have to build a separate model. Okay, so different NLP tasks, different deep learning models from scratch. So that was the state of the art in before 2017. Okay, all right. So now you might be wondering, earlier I showed you the concept of transfer learning, remember? So for images, right, with ALEXNet, VGG16, so these models were already trained on 1.2 million images on 1,000 categories. So I said through transfer learning, you can use these pre-trained models, right, and then fine-tune them on your own image classification tasks. We can do something like that here as well. And that is where we went from building these deep learning models from scratch to having a language model. Okay, let me explain a little bit more. So what is a language model? So again, these were some of the early offshoots of modeling language. Okay, so what exactly is a language model? At its core, it's simply a deep neural network model. Okay, as I said, these are all deep learning models. So how do you build this language model? As I said earlier, right, any model, if you want to build or train it, you have to feed a lot of data. That's what we're going to do here. So for language model, what are we going to feed? We're going to feed a lot of language. So in this language could be books, journal articles, different text corpuses. So a lot of language related data you can feed into this one. Okay, you feed all of this, you train this model. Again, you could use one of the architectures earlier I showed you, RNN, LSTM, any of these architectures, they will work. Okay, so you can train this language model, and then what you get is a pre-trained model, just like ALEXNET or VGG16, for image data. So we can get something like that for language also. So we get this pre-trained language model. So what does this pre-trained language model have? So what is this contain? What does this contain? Now see, now this pre-trained language model, it has already been trained on a lot of language. So it has some inherent knowledge of grammar, of phrases, right? So some semantics, some meaning. So think of somebody who has read millions and millions of books. So this language model has read all of this. So it has a general concept of language, it's understanding the language. But see, by understanding that language by itself was not enough. What we had to do was we still had to fine tune this language model, right, for different NLP tasks. What do you mean? So let's say you have different NLP problems like, question answering, summarization, sentiment. All of these are different NLP, natural language processing tasks. So if you want to use this language model, this one directly you can't use it, but you take this one and you fine tune this language model on each of these tasks. Then what you get a QA model, you get a summarization model, you get sentiment analysis model. See, this is still better because this we're still doing transfer learning, right? Because if you want to build a QA model from scratch, that would be computationally very intensive. Same thing with summarization model, sentiment model. But we could really take this pre-trained language model and then fine-tune it on a smaller QA dataset for QA model, or summarization dataset for summarization model, sentiment dataset, smaller sentiment dataset for a sentiment model. Hopefully you understand the concept, right? This was very similar to what we did with images. Again, this was the state of the art. Very recently, from 2017 to 2022, the state of the art was to use this pre-trained language models. Because now when we are going to pre-trained language models, we are not building the models anymore. The models are already built. Somebody built these models. We're going to use them and we're going to fine tune these models for different NLP tasks. So that was the state of the art in 2017 to 2022. Okay, now it's time to talk about one of the greatest discovery in AI, and that's transformer neural network architecture, transformers. In fact, it's the biggest breakthroughs in AI, but it won't be an exaggeration if I say this could have been the biggest breakthroughs of modern civilization too. I'm hoping some of you who are aware of this would agree with me, because this is what enabled all the magic, all the advancements, whatever the speed you are seeing with respect to AI, LLMs, agents, agentic AI, all of that is happening, of course, because of deep learning, but within deep learning, this particular neural network architecture, and this was given to us by Google. Kudos to them. Through this paper, attention is all you need. So this was a phenomenal, seminal paper that completely changed the landscape. I will explain in clearly, why. But basically, this paper gave us this transformer architecture in 2017. Now, some of you, again, looking at this architecture, might be, wow, this looks intimidating. Please don't be, as I said, all these deep learning models, the neural networks, inside they may look complicated, but intuitive level, it's very simple. I'm not going to explain this transformer architecture in detail in this one. That definitely warrants a separate video. I'm going to do that there. But for now, again, think you're still going from inputs to some output. It's still the same thing. And in the middle, you're doing all kinds of neural network architecture. Okay. So I just want to show you the original architecture as it is. Again, in a separate video, I'm going to explain the transformer architecture extremely in detail. That's my promise to you. Okay. All right. Now, based on this transformer architecture, some language models have come up in 2017. One of the famous was BERT, and the other famous was GPT-1. See, until these language models, there were language models before, but they were based on the RNN the architecture LSTM, which I discussed earlier, right? But BERT and GPT-1, soon after these transformer papers are published, these language models came. They all completely changed the state of the art of language models at that time. Again, these are based on transformers and they worked extremely well. But as I said, these are language models. At this stage, the language models, right? LLMs, right? They were pre-trained models. You can't directly use them for different NLP tasks. You had to fine-tune these. You can still use BERT if there is, let's say you have some data which is very proprietary, okay, which some of these foundational AI models you might be hearing, right? ChatGPT and all of that, right? They may not know that. If for a particular niche use case, you may still find that this BERT language model is very powerful, but you have to fine-tune it for your particular use case, okay? So, all right. So this was about the transformer architecture, the biggest breakthroughs in AI and modern civilization. Next, I'm going to explain why transformers are so powerful. Okay. Yeah. Why did they become so powerful? I mean, so powerful. Why is it the biggest breakthrough? To understand that, let me show you a sentence here. Again, for the explanation purpose, it's still a shorter sentence, but imagine this applies even more to long sentences. So if you see here, the movie that I watched last week, which everyone recommended and said was impressive, so far everything is positive, was actually not good. So what's happening? Like if somebody is reading this from left to right, initially it was impressive, but later towards when you went to the end, it was not good. But let's say, let's say if you're using some of the older model architecture, like RNN or LSTM, right? If you use this to model this sentence to predict sentiment, right? So again, if RNN or LSTM, even LSTM, you say the movie that I watched, as you keep going, you see its memory is going down. Again, this example is dramatic. LSTM may probably work well for this sentence. This is not that long, but I hope you understand. These older models, if it's a very long sequence, as you go down this sentence, some of the earlier words are fading. And by the time you reach not good, it lost the connection between movie and not good. It forgot that they are linked. So that was the problem with some of these older models. Another problem is these older models, whether it's RNN or LSTM, they looked at each word sequentially, right? One word at a time sequentially. Okay. That limited their ability to scale these architectures like RNN and LSTM for lot of sentences, lot of language. If you want to train a model on lot of language, right? You can't really scale because these architectures are going one word at a time, left to right, sequentially. And then came transformers, the new kid on the block in 2017. And it completely changed the game. Why? Because with transformers, the entire sentence, it sees the entire sentence, keeps all the context. What do I mean? You're not doing sequential processing anymore. Every word can attend to every word simultaneously. So suddenly, because that's how, right, we humans, right, when you're reading, yeah, you may read sequentially, but you keep the entire context, first word to last word, and then you form an opinion about that sentence, whether it's positive or negative. That's what transformer could do, of course, probably even more faster than we could. Every word attends to every word, and transformer architecture can see the entire sentence which you give it with all the context intact. And the result is that it knows that there's a strong connection between movie and not good, irrespective of the word impressive, recommended, or whatever comes in the middle. See, you could use machine learning approaches, something called bag of words, to build a sentiment model on this sentence. That could also work, right? But see, seeing impressive and recommended, machine learning would have got confused. But transformers, it clearly sees, because it sees the entire sentence, it knows that movie is not good. This is a negative. So this was one of the main things, the ability to self-attend. This was called self-attention. Every word can attend to itself and every word in the sentence simultaneously. Okay. So the main advantage of transformers, it worked beautifully for long sequences. LSTM overcame the long sequence limitations of RNN to some extent, but transformers truly overcame that limitation. As I said, simultaneous attention, every word could attend or see all the other words, how the relationship is. And because of this, since every word can attend to every word, and the transformer is looking at the entire sentence, right? Not sequentially, you could do parallel execution. And that means you can train much bigger models using much bigger data. So now, see, RNNs, LSTMs, they were able to train on some books, some articles, some journal articles, but now imagine, think bigger, right? Longer corpuses, lot of language data. Transformers, no problem. Again, with the help of GPUs, that again goes to scalability. Okay, so these were some of the powerful advantages of transformers, and most importantly performance, right? So not only we can build bigger models, larger models, scale more efficiently. Performance was again state of the art. It beat all the old models that were based on RNNs and LSTM. Okay, computationally though they are a little bit more intensive compared to the older models like RNN and LSTM. Okay, hopefully the previous slide and this one gave you a good understanding on a very high level, right? What transformers are, at least the power of transformers, what they're doing intuitively. Architecture wise, as I said, I'm going to cover that in more detail in a later in my deep learning playlist. Please check that one out. I'll put that in the description. Okay, all right, now it's an important moment. Let's see, we talked about machine learning, then we looked at deep learning. We looked at deep learning for images. We looked at deep learning for languages. I showed you that we could build this deep learning model from scratch, whether for images or language. But then we also talked about using pre-trained models, right? That's where with language model, right? You can use deep learning to build a language model like BERT or GPT-1, and then you take them and you fine tune them on different NLP tasks. And then we talked about this important transformer architecture. Now the question is, okay, so far we're talking ML, deep learning, language models. What is this LLM? Where did large language models come? How did that evolution happen? That's what we're going to talk here. Okay. So to explain this, I want to use this kind of a graph here or a chart. So on the x-axis, let's say we have model size, meaning how big, as I said, right? Because again, this also happened with transformers. Because of transformers, you could train your models with bigger and bigger data. Okay. So if I plot model size on this x-axis, right? If you go left to right, you're using bigger models. Okay. And on the y-axis, is performance. Okay. So these two axes. On the x-axis, you have model size. On the y-axis, you have performance. Okay. Now, between 2017 to 2022, again, the state of the art was to use pre-trained transformer-based language models, right? So we were using language models, and then we had to fine-tune them for different NLP tasks, right? This I already explained. Language models like BERT, GPT-1. They are pre-trained models, and again, they were trained on a lot of data. Okay, so the parameters or the weights which these models had approximately was 100 million parameters. Think about it again, it's a deep neural network, okay, based on transformers. But the key thing was they required fine-tuning, meaning you can't use BERT or GPT-1 directly, even though they're language models. You had to fine-tune them for different language tasks like question, answer, sentiment, summarization. I already explained. Okay. Now, because of this transformer architecture, now, as I said, you could train bigger and bigger models. The only limitation was the data, right? The data and the compute. But NVIDIA was providing GPUs, right? NVIDIA was inventing big time during this time. Okay. So using NVIDIA GPUs, people started training bigger models than, BERT and GPT-1. And what they noticed was as they started making these models, right? The model size, they kept going bigger and bigger. They started seeing, as you went, dramatic improvements in performance. Okay. As the model size became bigger, the performance of this language model started growing big. It started growing big in such a way that at an inflection point, it became exponential, the performance. And that gave us our 2022 ChatGPT moment. Hopefully you see what's happening here. Now, ChatGPT used the GPT 3.5 model. Again, we went from GPT-1. This is all from OpenAI. We went from GPT-1 to GPT 3.5. What is the difference between GPT-1 to GPT 3.5? The main difference was the scale, meaning the model size, right? So we started using bigger and bigger, data. For example, I think, let's say for ChatGPT, the GPT 3.5, when it's a massive data, think of worldwide internet data, all kinds of language data, humongous amounts of data. So you had a much bigger model. See, to keep it in context, Burton GPT was 100 million. ChatGPT was based on GPT 3.5, 175 billion parameters. You can think of the scale, right? Now again, when we say scale, it's not just the massive data, right? So again, for massive data, you are using large scale models and you're using tremendous amount of compute. Okay, so with all of this, right, we built ChatGPT. And whatever the saying, as you kept increasing the model size, right, there was an inflection in the performance, as you can see from this curve, right? There was an inflection. So what exactly happened? Well, as we increased the scale, as we started building bigger and bigger models, suddenly these language models became large language models with emergent abilities. That sounds amazing, right? Emergent abilities. What do we mean? Well, now GPT 3.5, it can do any NLP task without any explicit instruction. See, BERT and GPT-1, they are language models, but you have to fine tune them. We have to fine tune them for QA, sentiment summarization. But GPT 3.5, you don't need to fine tune. I mean, at least I will explain, the exact version of ChatGPT, Actually, GPT 3.5, yeah, you don't have to fine tune. So it could do any NLP task without explicit instruction. See, the key thing is nobody programmed these abilities. That's what emergent means. They just appeared when the model got big enough. Think about it. As we kept increasing the scale, these language models as they became large language models, they suddenly became super smart. They had these emergent abilities. They could do any NLP task with a simple prompt. I know. That's what, I guess, if many of you are studying in school, just finishing your master's or, in AI, in that sense, now you're all used to ChatGPT Cloud, right? You just give a prompt and you get the answer. That was what was enabled in 2022 with the advent of ChatGPT with this GPT 3.5 model. Amazing, right? So again, we say single prompt, or you could do multi-shot or few shot. You give the model few examples and it will, answer awesome, in an amazing manner, whatever the questions you ask it. You could do many different NLP tasks. Okay. Now, where we are is we have large language models. Again, we went from GPT 3.5. Today with OpenAI, we have GPT-5 version. Again, we have Cloud, another amazing competitor, a Gemini, all these leading LLMs. To put in context, now it's trillion parameters. Now, again, we don't know the exact number because a lot of these models are closed, so we don't know. But, we went from 100 million to around trillion parameters. Hopefully, this slide gave you a good understanding as to what exactly happened. These language models, when they became large language models because of scale, they got these emergent abilities. They became super smart. Okay. Now, I want to take a little bit more moment and explain ChatGPT moment a little bit more detail. Because scale is what gave it all of its abilities, most of its abilities, but that was not enough. So let me explain ChatGPT, the magic of ChatGPT, as to what was behind it. So let me give you an example. Let's say if a user asks, summarize this article for me. Okay. So ChatGPT is based on, so this is based on GPT 3.5. Okay. So before that, we had GPT-3. This was also 175 billion parameters. So this was already a big model because of scale, right? So we went from BERT or GPT-1 to GPT-3. So it was a big model, meaning it already had emergent abilities. So if your user asks this question, summarize this article for me. So it can do any NLP task. Okay, it can. So it would give something like this. The article discusses climate change, impacts on coastal regions, rising sea levels threaten millions of homes. Again, it says the article discusses climate change impacts on coastal regions, rising sea levels. It's kind of repeating, but if you see, it's doing the task. I mean, it's doing what we asked it to do. We asked it to summarize, it's summarizing us. Okay, so it was great for that moment because we didn't have to fine tune anything here, right? We just trained a bigger model and the bigger model could do this. So that was great. but still it's unpredictable, right? I mean, you're repeating stuff. Okay, so then what we did was, again, researchers, they took GPT-3 and they added supervised fine-tuning to it. So SFT, supervised fine-tuning, what is that? Well, they gave to GPT-3 human curated questions and answers. So human had some questions, human wrote some answers, right? More meaningful questions, more meaningful answers. They gave it to GPT-3 and fine-tuned it. And because of that, now the result is a little bit better. Right, it has more structure now. Climate change effects, course, sea levels are rising globally. It's summarizing the article in a neater fashion. So with the addition of SFT on GPT-3, we have now more structured, but still a little bit not robotic, but not completely helpful and conversational, right? So on top of this, what researchers did is with GPT-3 and supervised fine-tuning, they added another technique called reinforcement learning with human feedback, RLHF. Reinforcement learning with human feedback. Okay, what is that? Well, now here a human asks a question to the model and the model gives it responses, and of all the responses, human selects the ideal one. Okay, so for every question, we were collecting different responses and we're selecting the ideal responses, and we're using all of this to fine-tune this GPT-3 model with supervised fine-tuning. On top of that, we were doing this reinforcement learning with human feedback. So we're making the model more aligned to what humans want based on human preferences, and we created a data set for that and we fine-tuned this further. And now the result is, a more nice, helpful, conversational kind of summary. Sure, here is a quick summary. The article covers how, and so on. You get the idea. So now it's helpful, conversational, but most importantly, it's aligned with human preferences. So this was our ChatGPT moment. Okay, so this is our ChatGPT moment with GPT 3.5. November 2022, ChatGPT was released, and rest was history. So scale gave the genius, right? So scale by itself, scale means making models bigger and bigger. That gave us the initial genius. Supervised fine-tuning gave it structure, maybe a little bit conversational, but reinforced learning with human feedback made it ours based on our own preferences. So hopefully now, what happened with ChatGPT? How did we get, whatever amazing discovery or whatever the invention happened in 2022? The benefits, I'm pretty sure, we're all using either ChatGPT or, Cloud, another amazing foundational model, from Anthropic or Gemini, from Google. Okay. All right. So next, I'm going to talk about where we are with respect to the LLM world today. I already hinted, right? So these are all the choices because I just want to give you a high level landscape, right? Okay. So I have organized these LLMs into two categories, proprietary and open source. First, talk about proprietary. Again, OpenAI, right? It started the revolution. 900 million weekly users. This number keeps growing. Okay. I think the latest model is 5.2 or 5.4. Then we have Anthropic. Anthropic, trust me, recently it's growing in immense popularity, especially it's becoming the enterprise choice mainly for coding and reliability. Okay, there's a big competition going on between OpenAI and Anthropic. Then we have Google's Gemini. Again, Google gave us transformers, right? Google gave us transformers, the biggest invention that enabled all this AI revolution. That came from Google. But initially, Google was falling behind in this large language model. Again, BERT, right? One of the language models was from Google, but it kind of fallen behind OpenAI. But now, again, Gemini is in the top. Okay? It's deep inside search, Gmail, everywhere. Gemini is embedded. And then I just put XAI and Grok because this was from Elon Musk. Again, this is another competing model. It's built into, Twitter. Okay, so this is the proprietary landscape. What about open source? The open source, again, it's free to use and modify. Again, the leading one in terms of most used globally is Llama. That's from Meta, or Facebook. From Meta, we have Llama, and it had 10 million token context, meaning, again, you can put long context into the Llama model. And then you have DeepSeek from China. Okay, so the DeepSeek, this when it came, it completely shocked everybody, because it built GPT-4 quality, like from OpenAI, for only 6 million or some small amounts. So that was a big shock. Again, this came from China. Then you have Moonshot AI. From Moonshot AI, you have Kimi. So Kimi K2. So that was actually, I should have reversed this. So the actual LLM's name is Kimi K2. Okay. And this is a China's rising challenger. It is matching, some of the frontier models, right? So some of the frontier models, the performance of some of the frontier models. When I say frontier, these proprietary models, this Kimi K2 from Moonshot is kind of approaching that. So that's pretty amazing. And then we have Quen from Alibaba. It's one of the most downloaded family and Hugging Face in 2025 and 2026. Lot of competition is coming. There is another latest LLM from China. I think it's called GLM, which is again giving a big competition to some of this proprietary. So just wanted to give you on a high level, this landscape. Okay, again, you can see, right, most of the proprietary are from US, and a lot of open source leaders are from China, except our Llama, Meta, of course. Okay, so in this video, I just wanted to, because I've been taking you on a journey from data science to LLM. I quickly wanted to show you what is the LLM world choice out there now. Which of this model is best? Which model to use when? Of course, that will be beyond the topic of this video, but it's my promise I'm going to cover in a later video. Again, so please subscribe to the channel, right? So that you can get that video in time when I make that video. Okay. So this was on a high level, the LLM world that we have today. But see, we're not done. Okay. We have one more important concept to cover. How did we go from LLMs to AI agents? This is the next biggest leap, and it's happening right now. This is the bleeding edge, right? So agents is the bleeding edge of AI right now, and it's happening now. So quickly, I want to show you what we mean agents compared to LLMs. So let's say, I said before, but again, we're still using LLMs. But if you have an LLM, right, large language model, how does it work? Well, we ask it questions and it responds. So let's say if I ask this large language model, which company leads the drone industry? So what it's going to do is it's going to answer me. It's going to give me some information on the leading company. Let's say, but the important thing is it's giving me this information based on the cutoff, the training cutoff, right? So all these LLMs have a training date cutoff. So whenever this LLM was trained, based on that information, it's giving me this information. It's not searching the latest information. So we ask the question, it responds, but it can answer only based on the information it already has. Then we ask which other companies dominate this market. Again, it's like, here is a summary of the companies. Prepare a comparison and summarize. We ask, and it will give us a summary. So basically, we're asking the question, and the LLM responds. Okay. Now, the state of the art right now is, okay, this LLM is simply responding to a request based on some old cutoff knowledge, right? What if we can give it some tools so that maybe it can search web, right? Maybe it can use different tools to get the information we want. Okay. And while we're doing that, why don't we give it some memory so it can have a good remembrance of the conversation and of everything that we're doing. And on top of that, if we can give it the ability to plan, right, we can give some workflow as to how it can plan, or if we can give it full autonomy. So we'd give it some tools, give it some memory, give it the ability to plan, and give it the autonomy. What we have is an agent. Sounds amazing, right? So with an agent though, now if you see here, right, you can simply ask research top 5 competitors in drones and prepare a strategy brief, put it in my inbox by 3 p.m. It's going to do all of that. It's going to search the web for all 5 competitors. Again, it's going to use one of the tools for web search, let's say. It's going to read their pricing on product pages, identify the gaps, writes brief, and it's going to put it in our inbox. So again, agent is going to use different tools, web or maybe email, calendar, files, API, you name it, right? So hopefully you can see what's happening here. With agent, we don't just prompt, we delegate. Again, this is the bleeding edge happening right now There are many amazing agentic frameworks that are getting developed. Again, all of that is a concept for a later video. But the key here is it's the same intelligence between LLM and agent, but now the ability to act we are enabling it with additional tools, memory, and planning so that it can act on our behalf. With an LLM, we give instructions. With an agent, we give a goal and we walk away. This is 2026 and beyond. Okay, all right. Okay, so we finally are towards the end of this video. You came into this video maybe a little confused, not knowing how all these different buzzwords connected, starting with data science and the entire landscape. Hopefully this video help you a little bit in understanding how everything connects. Again, we started with, data science, defining what data science is. Harvard Business Review called it the sexiest job in, 2012. And the point here is classical ML, right? Classical ML dominated data science at that time. It's still important, okay? ML is still important, but it was the dominating approach in 2012 in data science. And then in 2016, deep learning announced itself to the world, proved its worth, again through some amazing architectures, CNNs for images, convolutional neural nets, recurrent neural networks, those were the architectures which initially modeled language. Again, deep learning was the dominating approach in 2016. And then one of the biggest breakthroughs happened in AI. Again, as I said, it won't be an exaggeration, right? Transformers, through this paper, attention is all you need from Google, pretty much change everything in AI. In fact, not only AI, I think it changed the world as we speak, because with all the amazing developments, whatever we see today that's happening in AI, whether it's a language model, image model, foundational model, LLM, any kind of LLM agents, the foundation is deep learning, but within deep learning, it's transformer architecture. So this is one of the, phenomenal moment in history when transformers was given to us, by Google. And in 2018-ish time frame, again, we had, BERT and GPT-1, one of the earlier language models that were built using the transformer architecture, and they beat the competition, the state-of-the-art competition at that time with older RNN, LSTM-based neural network architectures. Again, BERT, GPT-1, one of the earlier language models, but we had to fine-tune them. We could not use BERT or GPT-1 for any NLP task, with a single prompt. You had to fine-tune them for different NLP tasks. Okay, but that paved the way for another amazing, again, breakthroughs of our time with ChatGPT. So if I have to say, I think these two are really key. When transformers came in 2017 and in 2022, ChatGPT. Again, ChatGPT is also based on transformers, but the difference between ChatGPT and GPT-1, so ChatGPT was, as I said, was based on GPT 3.5 model. Right? That's what ChatGPT was based on. So scale gave these LLMs emerging abilities, meaning they could do any NLP task because of the scale. Again, when I say scale, they were trained on much larger volumes of data using bigger models, larger compute, and because of the scale, they got emergent abilities, meaning nobody programmed them, right? And they could do any NLP task with a single prompt. And we know what happened after that. It's history, right? We're all witnessing it. We're all using ChatGPT. Okay, so this was another amazing moment. Actually, in 2016, actually not 2016, in somewhere around, again, 2012, right, we got ALEXNET. Again, this was still in deep learning. It just, in 2012, ALEXNET showed the power of, deep learning. And by 2016, deep learning completely took over. So that was also another phenomenal moment I have to mention. When ALEXNET came and when transformers came and with ChatGPT. Okay, and now, from 2023 onwards, it was all LLM eras. GPT models kept improving, 3.5, 3.4, GPT-5 now. Cloud became another amazing competitor. Gemini, Llama, proprietary, open source LLMs. And today, again, for the past 2 years, it's all been agents, right? We delegate, they act. Okay, so we are here now. Hopefully, you felt a little better, understanding this entire landscape, how AI evolved, where we started, and where we are today. Okay, so I'm sure, right? It may not have answered all the questions, but at least a little bit now. Some of these buzzwords, they appear not so disjointed, and you can see the connection. But you may have one more doubt, right? Which of these is still relevant and useful? Well, a AI practitioner, or a data scientist may use one of these or all of these in some form or the other. So just because I listed classical ML in 2012 doesn't mean it disappeared now, or deep learning has disappeared. No. So all of these are still relevant. So depending upon the use case, depending upon the problem, some practitioner may use classical approach to solve a problem, to build a model. Some other scientist or AI practitioner may still build deep learning models from scratch, depending upon their particular use case. Or somebody may use LLMs. When you are saying LLMs and agents, right, we are using these models. For most purposes, we're not building them. We're using them in inference mode. And most of the action that's happening over the past 2 years is using these LLM models, using the agents to build different software applications or make our life easy. Now, which of this solution approach is useful for what use case? I know that's a question in your mind. This video has already become very big. But it's my promise, I'm going to cover this topic in detail in a later video. Okay. But for now, the key takeaway I want you to have is we went from models that can predict, again with machine learning, the shallow machine learning algorithms and deep learning algorithms, to models that can respond, right? So we went from prediction to respond through an LLM. But again, the key point is we built LLM using deep learning. So all LLMs you see, they are built using deep learning. So we went from models that can predict to models that can respond to now the model that can act through agents. So that's the journey so far. Again, hopefully this video made it a little bit clear to see how everything connects. But see, the real question is still, where do you fit in the map? Where do you fit in this journey? What do you actually need to learn? What should you learn first, and in what order? What AI learning path is right for you? So these are all the questions that you may still have, and I understand, and it's my promise to answer all these things in detail, make it easy, because now that you have seen how this entire field evolved, how all these buzzwords are connected, in the next video, I'm going to take you deeper into the AI learning path. Right? What are the things that you can actually learn, and maybe in what order, and where do you exactly fit? And this is my promise to you. I'm going to do that in the next video. But if you like this video so far, please like, please share, and please don't forget to subscribe, because so that you don't have to miss the next video I'm going to release. Okay. Thank you so much for watching this long video with patience. Hopefully I helped you a little bit in understanding how all these things are connected. Happy learning. Please stay tuned. We'll see you in the next video. Thank you so much.